Quantum physics is a physical science managing the conduct of matter and energy depending upon the size of atoms and subatomic particles/waves. It likewise frames the basis for the contemporary comprehension of how huge objects, for example stars and universes, and cosmological events, for example the Big Bang, can be analyzed and clarified. Quantum physics is the establishment of a few related orders including nanotechnology, dense matter material science, quantum science, basic science, molecule material science, and gadgets. The expression quantum mechanics was initially authored by Max Born in 1924. The acknowledgement by the general physics group of quantum mechanics is because of its exact forecast of the physical conduct of frameworks, including systems where Newtonian mechanics come up short. Indeed, even general relativity is restricted, in ways quantum mechanics is not, for portraying systems at the nuclear scale or lower level, at low or high energies, or at the most minimal temperatures. During a time of experimentation and connected science, the quantum mechanical theory has ended up being exceptionally fruitful and viable. The establishments of quantum mechanics date from the mid-1800s, yet the genuine beginnings of QM date from the work of Max Planck in 1900. Albert Einstein and Niels Bohr soon made critical commitments to what is currently called the old quantum hypothesis. In any case, it was not until 1924 that a more finished picture rose with Louis de Broglie's matter-wave theory, and that the genuine significance of quantum mechanics turned out to be clear. Probably the most conspicuous researchers to work along these lines contribute in the mid-1920s to what is presently called the new quantum mechanics, or new material science, were Max Born, Paul Dirac, Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger. Later, the field was further extended with work by Julian Schwinger, Sinitirio Tomanonga, and Richard Feynman for the improvement of quantum electrodynamics in 1947, and by Murray Gell-Mann, specifically for the advancement of quantum chromodynamics. The impedance that produces colored bands on bubbles can't be clarified by a model that portrays light as a molecule. It can be clarified by a model that delineates it as a wave. The drawing demonstrates sine waves that look similar to the waves on the surface of water, being reflected from two surfaces of a film of fluctuating width. However, that depiction of the wave pathway of light is just a rough relationship. Early specialists contrasted in their clarifications of the major way of what we now call electromagnetic radiation. Some kept up that light and different frequencies of electromagnetic radiation are made out of particles, while others attested that electromagnetic radiation is a wave marvel. In traditional material science, these thoughts are commonly conflicting. Following the time when the beginning of QM researchers has recognized that no single idea can independently clarify electromagnetic radiation. Regardless of the achievement of quantum mechanics, it has some dubious components. For instance, the conduct of microscopic items portrayed in quantum mechanics is altogether different from our regular experience, which may incite some level of doubt. The vast majority of classical physics is currently perceived to be made out of uncommon instances of quantum physics theory and/or relativity hypothesis. Dirac offered relativity theory as a powerful influence on quantum physics, so it could appropriately manage occasions that happen at a significant portion of the rate of light. Classical physics, nonetheless, additionally manages mass fascination, gravity, and nobody has yet possessed the capacity to carry gravity into a bound-together hypothesis with the relativized quantum hypothesis. What you need to know about quantum physics. Quantum physics seems to scare from the get-go. It's sort of unusual and can appear to be peculiar, also for the physicists who manage it consistently. In any case, it's not unlimited. In case you're perusing something about quantum physics, there are 6 key ideas about it that you need to remember. Do that and you'll discover quantum physics a lot less demanding to understand it. Everything is made of waves, also particles. There are several places to begin this kind of discussion, and this is comparable to any. Everything in the universe has both molecule and wave nature at the present time. There's a line in Greg Bear's fantasy duology, The Infinity Concerto and the Serpent Mage, where a character portraying the enhancements of magic says, "All is waves with nothing waving over no distance at all." It is generally preferred as a lovely depiction of quantum physics. Where it counts, everything in the universe has wave nature. Obviously, everything in the universe additionally has molecule nature too. This appears to be totally fanatical, but from the experimental point of view, it has been worked out by an amazingly recognizable procedure. Obviously, portraying real particles as both particles and waves is fundamental to some degree imprecise. If speaking scientifically, the items depicted by quantum physics are neither particles nor waves. However, a third classification that shares a few properties of waves, a characteristic frequency and wavelength, some spread over space, and a few properties of particles. They're for the most part countable and can be limited to some degree. This prompts some exuberant debate inside the physics training group about whether it's truly fitting to discuss light as a molecule in introduction physics courses, not on the grounds that there's any contention about whether light has some molecule nature, but since calling photons particles, as opposed to excitations of a quantum field, may prompt some understudy confusions. This doorway 3 nature of quantum objects is reflected in the occasionally befuddling language physicists make use of to discuss quantum wonders. The Higgs boson was found at the Large Hadron Collider as a molecule, yet you will likewise hear physicists discuss the Higgs field as a delocalized thing filling all of the space. This happens in light of the fact that in a few circumstances, for example, collider experimentations, it's more advantageous to talk about excitations of the Higgs field in a way that stresses the molecule-like attributes, while in different circumstances, similar to general exchange of why certain particles have mass, it's more helpful to examine the physics as far as connections with the universe-filling quantum field. It's simply distinctive language portraying the same mathematical item. Quantum physics is discrete. How come you come to the conclusion that this branch of physics is discrete? Well, if you look close, it is right there in the name quantum, which originated from the Latin for how much, and mirrors the way that quantum models dependably include something coming in discrete sums. The energy contained in a quantum field comes in whole number products of some major energy. For light, this is connected with the frequency and wavelength of the light. High frequency, short wavelength light has an expansive characteristic energy, which low frequency, long wavelength light has a little characteristic energy. In both cases, however, the combined energy contained in a specific light field is a number different of that energy, 1, 2, 14, 137 times, never an odd portion like 1.5 pi or the square base of 2. This property is additionally found in the discrete energy levels of molecules and the energy groups of solids. Certain estimations of energy are permitted, others are definitely not. Why do atomic clocks work? As a result of the discreteness of quantum physics, utilizing the recurrence of light connected with the move between two permitted states in cesium to keep time at a level requiring the highly talked about leap second. Ultra-exact spectroscopy can likewise be utilized to search for things like dark matter, and is a piece of the inspiration for a low-energy major physics institute. This isn't generally obvious. Even a few things that are essentially quantum, similar to dark body radiation, seem to include ceaseless distributions. In any case, there's dependably a sort of granularity to the fundamental reality in the event that you dive into the science, and that is a huge part of what prompts the irregularity of the hypothesis. Quantum physics is probabilistic. A standout amongst the most astounding, and verifiably in any event dubious part of quantum physics is that it's difficult to anticipate with assurance the result of a single investigation on a quantum framework. At the point when physicists anticipate the result of some trial, the expectation dependably takes the type of likelihood for finding each of the specifically conceivable results and correlations amongst hypotheses, and examination dependably include surmising likelihood appropriations from numerous revised tests. The numerical portrayal of a quantum framework commonly takes the type of a wave function, for the most part spoke to in conditions by the Greek letter psi. There's a great deal of open debate about what, precisely, this wave function speaks to, separating into two principal groups: the individuals who think about the wave function as a genuine physical thing. The language term for these is ontic hypotheses, driving some witty individual to name their advocates psi-cosmologists, and the individuals who think about the wave function as just an outflow of our insight, or deficiency in that department, in regards to the fundamental condition of a specific quantum object, epistemic speculations. In either class of foundational model, the probability of finding a result is not given straightforwardly by the wave function, but rather by the square of the wave function. Freely at any rate, the wave function is a complex numerical article, which means it includes non-existent numbers like the square base of -1, and the operation to get likelihood is somewhat more included, yet square of the wave function is sufficient to get the fundamental idea. This is known as the Born rule, after German physicist Max Born, who initially proposed this, in a reference to a paper in 1926, and strikes some individuals as an appalling specially appointed expansion. There's a dynamic exertion in some parts of the quantum establishments group to figure out how to get the Born rule from a more central guideline. To date, none of these have been completed fruitfully. However, it creates a considerable measure of fascinating science. This is likewise the part of the hypothesis that prompts things like particles being in different states in the meantime. Everything we can anticipate is a likelihood, and before an experiment that decides a specific result, the framework being measured is in a vague form that scientifically maps to a superposition of all conceivable outcomes with various probabilities. Whether you consider this as the framework truly being in the greater part of the states without a moment's delay, or simply being in one obscure state, depends generally on your emotions about ontic versus epistemic models. However, these are both subject to requirements from the following thing on the rundown. Quantum physics is non-local. The last amazing contribution Einstein made to physics was not generally perceived in that capacity, for the most part since he wasn't right. In a 1935 paper with his young colleagues Boris Podolsky and Nathan Rosen, the EPR paper, Einstein gave an unmistakable numerical articulation of something that had been disturbing him for quite a while, an idea we now call entanglement. The EPR paper contended that quantum physics permitted the presence of frameworks where estimations made at broadly isolated areas could correspond in ways that proposed the result of one was controlled by the other. They contended that this implied the estimation results must be resolved ahead of time by some basic elements, in light of the fact that the option would require transmitting the after effect of one measurement to the area of the other at paces speedier than the velocity of light. Therefore, quantum mechanics must be inadequate, an unimportant estimation to some more profound hypothesis, a local hidden variable theory, one where the after effects of a specific measurement don't rely upon anything more distant far from the measurement area than a sign could go at the velocity of light, neighborhood, however, are dictated by some component basic to both frameworks in a trapped pair, the hidden variable. This was viewed as an odd reference for around 30 years, as there appeared to be no real way to test it. However, in the mid-1960s, the Irish physicist John Bell worked out the results of the EPR paper in more noteworthy point of interest. Chime demonstrated that you can discover circumstances in which quantum mechanics predicts relationships between far-off measurements that are more grounded than any conceivable hypothesis of the sort favored by E, P, and R. This was tried tentatively in the mid-1970s by John Clauser, and a progression of investigations by Alan Aspect in the mid-1980s is generally considered to have absolutely demonstrated that these entrapped frameworks can't in any way, shape, or form be clarified by any nearby local hidden variable hypothesis. The most well-known way to deal with the understanding of this outcome is to say that quantum mechanics is non-nearby, that the consequences of estimations made at a specific area can rely upon the properties of far-off particles in a way that can't be clarified utilizing signals moving at the rate of light. This doesn't, in spite of, allow the sending of data at velocities surpassing the pace of light. However, there have been many numbers of endeavors to figure out how to utilize quantum non-region. Negating these has ended up being a shockingly beneficial enterprise. Quantum non-area is likewise vital to the issue of data in dissipating dark gaps and the firewall contention that has created a ton of late movement. There are even some radical thoughts, including a scientific association between the entangled particles portrayed in the EPR paper and wormholes. Quantum physics is mostly very small. Quantum physics has a name of being unusual in light of the fact that its expectations are significantly not at all like our ordinary experience. This happens in light of the fact that the impacts included getting littler as objects get larger. On the off chance that you need to see unambiguously quantum conduct, you essentially need to see particles acting like waves, and the wavelength diminishes as the force increases. The wavelength of a plainly visible object like a pooch strolling over the room is so incredibly small that in the event that you extend everything so that a single molecule in the room were the span of the whole solar system, the puppy's wavelength would be about the extent of a single atom of that solar system. This implies generally, quantum wonders are restricted to the size of atoms and basic particles, where the masses and speeds are sufficiently little for the wavelengths to get sufficiently enormous to watch specifically. There's a dynamic exertion in many areas, however, to push the span of frameworks demonstrating quantum impacts up to bigger sizes. Quantum physics is not magic. The past point leads normally into this one. As irregular as it might appear, quantum physics is most insistently not magic. The thing it predicts are unusual by the norm of ordinary physics, however they are thoroughly obliged by surely new scientific standards and principles. Thus, in the event that some individual comes up to you with a quantum idea that appears to be too great to be true, free energy, mystical mending powers, inconceivable space drives, it is more likely not than is. That doesn't mean we can't utilize quantum physics to do stunning things. You can discover some truly cool physics in everyday technology, except those things stay well within the limits of the laws of thermodynamics and obviously basic common sense. Application of quantum theory. The implementations of quantum theory are far-reaching. Quantum mechanics has clarified the structure of the atom as well as the structure of the nucleus. Without knowing the structure of the atom, the vast concepts of the physics and science that we know today wouldn't have been conceivable. Quantum hypothesis anticipated the presence of antimatter and clarifies radioactivity. Numerous applications coming about because of the quantum hypothesis are being used today, and its applications later on are conceivably vast. The theory of lasers was initially sketched out in 1917 in a paper on the quantum theory of radiation by Albert Einstein, and the principal useful lasers were implicit in the 1950s. Quantum theory wisely clarifies the photoelectric impact, whereby electrons are discharged from matter as an after effect of absorbing energy from light. This happens in human vision and has got practical applications in digital cameras. Quantum physics is similarly utilized as a part of night vision goggles and examining burrowing magnifying lenses, which makes pictures of surfaces where single molecules can be seen. Several applications being developed that may have more prominent use later on include quantum entanglement. It is a wonder where two particles are quantumly connected to each other, paying little respect to how far separated they are. Disrupting any one of the particles additionally disrupts the other. This guideline has been utilized to encode data as any endeavor to catch one of the particles that will disturb the other, which can then be distinguished. Quantum computing. This utilizes the property that quantum particles can exist in various states in the meantime, so can be utilized to do numerous estimations in parallel. As of now, little quantum PCs have been made, yet at present there are technical challenges to be faced in building greater frameworks. Ultra-precise clocks. Steady timekeeping is about more than simply your morning clock. Clocks synchronize your innovative world, keeping things like security exchanges and GPS frameworks in line. Standard clocks utilize the normal motions of physical items like pendulums or quartz precious stones to create their ticks and talks. Today, the most exact checks on the planet, nuclear clocks, can utilize standards of quantum theory to quantify time. They screen the particular radiation frequencies expected to make electrons jump between energy levels. The Quantum Rationale Clock at the U.S. National Institute of Standards and Technology, NIST, in Colorado, just loses or picks up a second every 3.7 billion years. What's more, the NIST strontium clock, disclosed recently, will be that precise for 5 billion years, longer than the present age of the Earth. Such super-delicate nuclear tickers help with GPS route, information transfers, and looking over. The exactness of nuclear clocks depends halfway on the quantity of particles utilized. Kept in a vacuum chamber, every molecule autonomously measures time and watches out for the arbitrary nearby contrasts amongst itself and its neighbors. On the off chance that researchers pack 100 times more molecules into a nuclear clock, it gets to be 10 times more exact. Yet there is a cutoff on which number of particles you can crush in. Scientists' next enormous objective is to effectively utilize trap to improve exactness. Ensnared molecules would not be distracted with neighborhood contrasts and would rather exclusively measure the progression of time, adequately uniting them as a solitary pendulum. That implies including 100 times more particles into a snared clock would make it 100 times more exact. Entangled clocks could even be connected to frame an overall system that would quantify time free of the area. Uncrackable codes. Conventional cryptography works utilizing keys. A sender utilizes one key to encode data, and a beneficiary uses another to translate the message. Be that as it may, it's hard to evacuate the danger of a busybody, and keys can be traded off. This can be settled utilizing possibly unbreakable quantum key dispersion, QKD. In QKD, data about the key is sent by means of photons that have been arbitrarily spellbound. This limits the photon with the goal that it vibrates in standout plane, for instance here and there or left to right. The beneficiary can utilize captivated channels to decode the key, and after that utilization, a picked calculation to safely encode a message. The mystery information still gets sent over typical correspondence channels, yet nobody can disentangle the message unless they have the careful quantum key. That is dubious on the grounds that quantum decides manage that perusing the captivated photons will dependably change their states, and any endeavor at listening cautiously will warn the communicators to a security break. Today, organizations, for example, BBN Technologies, Toshiba, and ID Quantique, use QKD to plan ultra-secure systems. In 2007, Switzerland experimented with an ID Quantique item to give a carefully designed voting framework along with a decision. Furthermore, the main bank exchange utilizing COT QKD proceeded as a part of Austria in 2004. This framework guarantees to be very secure on the grounds that if the photons are snared, any progressions to their quantum states made by intruders would be instantly obvious to anyone observing the key-bearing particles. In any case, this framework doesn't yet work over expansive distances. In this way, caught photons have been transmitted over a most extreme separation of around 88 miles. Super powerful computers. A standard computer encodes data as a string of double digits or bits. Quantum computers supercharge preparing power since they utilize quantum bits or qubits, which exist in a superposition of states, until they are measured, Qubits can be both 1 and 0 in the meantime. This field is still being developed, yet there have been ventures in the right heading. In 2011, D-Wave Systems uncovered the D-Wave 1, a 128-qubit processor, took after a year by the 512-qubit D-Wave 2. The organization says that these are the world's first financially accessible quantum computers. Be that as it may, this case has been met with suspicion to some extent since it's indistinct whether D-Wave qubits are ensnared. In May, several studies have been released, discovered proof of entanglement, however just in a little subset of the computer's qubits. There's likewise instability about whether the chips show any solid quantum speedup. Still, NASA and Google have collaborated to shape the Quantum Artificial Intelligence Lab in view of a D-Wave 2. Also, at the University of Bristol a year ago, captured one of their conventional quantum chips to the internet so anybody with a web program can learn quantum coding. Enhanced microscopes. In February, a group of scientists at Japan's Hokkaido University built up the world's first entanglement-enhanced microscope, utilizing a method known as differential obstruction contrast microscopy. This kind of magnifying lens fires 2 light emissions at a substance and measures the obstruction design made by the reflected shafts. The example changes relying upon whether they hit a level or uneven surface. Utilizing captured photons incredibly expands the measure of data the microscope can assemble, as measuring one caught photon gives data about its accomplice. The Hokkaido group figured out how to picture an engraved cube that stood only 17 nanometers over the foundation with remarkable sharpness. Comparable systems could be utilized to enhance the determination of space sciences apparatuses called interferometers, which superimpose diverse waves of light to better break down their properties. Interferometers are utilized as a part of the chase for extrasolar planets to test nearby stars and to look for swells in space-time called gravitational waves. Natural compasses. People aren't the main ones making use of quantum mechanics. One driving hypothesis proposes that winged animals like the European robin utilize the spooky activity while migrating to keep the track. The strategy includes a light delicate protein called cryptochrome, which may contain captured electrons. As photos enter the eye, they hit the cryptochrome particles and can convey enough energy to break them apart, framing 2 receptive atoms or radicals with unpaired yet at the same time captured electrons. The attractive field encompassing the bird impacts to what extent these cryptochrome radicals last. Cells in the bird's retina are thought to be exceptionally sensitive to the nearness of the trapped radicals, permitting the creature to viably see an attractive guide in light of the particles. This procedure isn't fully seen. However, there is another alternative. Birds' attractive affectability could be because of little gems of magnetic minerals in their noses. Still, if entrapment truly is at play, tests recommend that the sensitive state should last any longer in an elevated than in even the best counterfeit frameworks. The magnetic compass could likewise be relevant to specific reptiles, scavengers, creepy crawlies, and even a few warm-blooded creatures. Case in point, a type of cryptochrome utilized for the attractive route as a part of flies has additionally been found in the human eye, in spite of the fact that it's vague in the event that it is or once was valuable for a comparative reason. Importance of quantum physics. In this chapter are discussed the most imperative things which quantum mechanics can portray while classical physics can't. Discreteness of energy. On the off chance that you take a look at the range of light radiated by vivacious atoms, for example, the orange-yellow light from sodium vapor streetlights, or the blue-white light made from mercury vapor lights, you will see that it is made out of individual lines of various colors. These lines speak to the discrete energy levels of the atoms in those energized atoms. At the point when an electron in a high energy state bounces down to a lower one, the molecule radiates a photon of light, which relates to the precise energy contrast of those 2 levels, protection of energy. The greater the energy distinction, the more vigorous the photon will be, and the nearer its shading will be to the violet end of the spectrum. On the off chance that electrons were not confined to discrete energy levels, The range from an energized atom would be a constant spread of colors from red to violet with no individual lines. The idea of discrete energy levels can be exhibited with a three-way light. A 40, 75, 115 watt bulb can just sparkle light at those 3 wattages, and when you change starting with one setting then onto the next, the energy instantly bounces to the new setting rather than just progressively expanding. The true electrons can just exist at discrete energy levels, which keep them from spiraling into the nucleus as classical physics predicts. Also, it is this quantization of energy, alongside some other nuclear properties that are quantized, which gives quantum mechanics its name. The wave-particle duality of light and matter. In 1690, Christian Huygens guessed that light was made out of waves, while in 1704, Isaac Newton clarified that light was made of small particles. Experiments upheld each of their speculations. In any case, neither a totally molecule hypothesis nor a totally wave hypothesis could clarify the greater part of the marvels connected with light. So scientists started to consider light both a molecule and a wave. In 1923, Louis de Broglie estimated that a material molecule could likewise display wave-like properties, and in 1927 it was appeared by Davison and Germer that electrons can in reality act like waves. In what capacity can something be both a molecule and a wave in the meantime? First and foremost, it is wrong to consider light a stream of particles climbing and down in a wave-like way. Really, light and matter exist as particles. What carries on like a wave is the likelihood of where that molecule will be. The reason light now and then seems to go about as a wave is on account of we are seeing the aggregation of a considerable lot of the light particles dispersed over the probabilities of where every molecule could be. Quantum tunneling. This is a standout amongst the most intriguing marvels to emerge from quantum mechanics. Without it, computer chips would not exist and a personal computer would presumably take up a whole room. As expressed over, a wave decides the likelihood of where a molecule will be. At the point when that likelihood wave experiences an energy boundary, the vast majority of the wave will be reflected back. However, a little partition of it will spill into the obstruction. On the off chance that the hindrance is sufficiently little, the wave that spilled through will proceed on the opposite side of it. Despite the fact that the molecule doesn't have enough energy to get over the boundary, there is still a little likelihood that it can tunnel through it. The Heisenberg uncertainty principle. Individuals are acquainted with measuring things in the macroscopic world around them. Somebody hauls out a measuring tape and decides the length of a table. A state trooper points his radar firearm at an auto and recognizes what course the auto is going, and in addition how quick. They get the data they need and don't stress whether the estimation itself has changed what they are measuring. All things considered, what might be the sense in verifying that a table is 80 centimeters long if the very demonstration of measuring it changed its length? At the nuclear size of quantum mechanics, in any case, estimation turns into an extremely sensitive procedure. Suppose you need to discover where an electron is and where it is going. That trooper has an inclination that any electron he finds will go quicker than the nearby speed limit. How do you do that? Get a super powerful magnifier and search for it? The very demonstration of looking relies on light, which is made of photons, and these photons could have enough force that once they hit the electron, they would change its course. It resembles rolling the signal ball over a billiard table and attempting to find where it is passing by skipping the 8-ball off of it. By making the estimation with the 8-ball, you have unquestionably modified the course of the prompt ball. You may have found where the signal ball was, yet now have no clue about where it is going. In light of the fact that you were measuring with the 8-ball rather than really taking a gander at the table. Werner Heisenberg was the first to understand that specific sets of estimations have a natural instability connected with them. For example, on the off chance that you have a smart idea of where something is found, then to a specific degree, you should have a poor idea of how quick it is moving or in what bearing. We don't see this in ordinary life in light of the fact that any natural instability from Heisenberg's rule is well inside the adequate exactness we want. For instance, you may see a stopped auto and think you know precisely where it is and precisely how quick it is moving. Be that as it may, would you truly know these things in particular? If you somehow happened to quantify the position of the auto to an exactness of a billionth of a centimeter, you would attempt to gauge the positions of the individual molecules which make up the auto, and those atoms would wiggle around on the grounds given that the temperature of the auto was above total zero. Heisenberg's instability guideline totally goes against classical physics. All things considered, the very establishment of science is the capacity to gauge things precisely, and now quantum mechanics is stating that it's difficult to get those estimations definite. In any case, the Heisenberg instability rule is a certainty of nature, and it is difficult to construct a measuring gadget which could get around it. Spin of a particle. In 1922, Otto Stern and Walther Gerlach performed a trial whose outcomes couldn't be clarified by classical physics. Their trial showed that nuclear particles have an inborn rakish force, or turn, and that this twist is quantized. That is, it can just have certain discrete qualities. The twist is a totally quantum mechanical property of a molecule and can't be clarified in any capacity by traditional material science. Realize that the twist of a nuclear molecule is not a measure of how it is turning. Truth be told, it is difficult to tell whether something as little as an electron is turning by any means. Spin is only a helpful method for discussing the inborn rakish force of a molecule. Magnetic resonance imaging, MRI, utilizes the fact that under certain conditions the spin of hydrogen nucleus can be flipped, starting with one state then on to the next. By measuring the area of these flips, a photo can be shaped of where the hydrogen molecules, principally as a piece of water, are in a body. Since tumors have a tendency to have an alternate water focus from the encompassing tissue, they would emerge in such a photo. We believe that now you clearly understand the term quantum physics as well as its importance and implementations. Quantum physics, being a branch of science, is a very interesting topic which motivates so many youngsters to study it and brighten up their future by making useful discoveries.